In recent years, engineers have found ways to modify the properties of some two-dimensional materials which are just one or a few atoms thick by stacking two layers together and rotating one slightly in relation to the other. This creates what are known as moiré patterns, where tiny shifts in the alignment of atoms between the two sheets create larger scale patterns. It also changes the way electrons move through the material in potentially useful ways. But for practical applications, such two-dimensional materials must at some point connect with the ordinary world of 3D materials. An international team led by MIT researchers has now come up with a way of imaging what goes on at these interfaces down to the level of individual atoms, and of correlating the moiré patterns at the 2D 3D boundary with the resulting changes in the material's properties. The new findings are described in the journal Nature Communications. Pairs of two-dimensional materials such as graphene or hexagonal boron nitride can exhibit amazing variations in their behavior when the two sheets are just slightly twisted relative to each other. That causes the chicken wire-like atomic lattices to form moiré patterns, the kinds of odd bands and blobs that sometimes appear when taking a picture of a printed image or through a window screen. While these 2D pairings have attracted scientific attention worldwide, little has been known about what happens where 2D materials meet regular 3D solids. Figuring out exactly what happens at such 2D 3D interfaces was a daunting challenge because electron microscopes produce an image of the sample in projection, and they are limited in their ability to extract depth information needed to analyze details of the interface structure. But the team figured out a set of algorithms that allowed them to extrapolate back from images of the sample, which look somewhat like a set of overlapping shadows, to figure out which configuration of stacked layers would yield that complex shadow. The team made use of two unique transmission electron microscopes at MIT that enable a combination of capabilities that is unrivaled in the world. In one of these instruments, a microscope is connected directly to a fabrication system so that samples can be produced on site by deposition processes and immediately fed straight into the imaging system. This is one of only a few such facilities worldwide, which use an ultra-high vacuum system that prevents even the tiniest of impurities from contaminating the sample as the 2D 3D interface is being prepared. The second instrument is a scanning transmission electron microscope. This microscope has outstanding stability for high-resolution imaging as well as multiple imaging modes for collecting information about the sample. Unlike stacked 2D materials, whose orientations can be relatively easily changed by simply picking up one layer, twisting it slightly and placing it down again, the bonds holding 3D materials together are much stronger, so the team had to develop new ways of obtaining aligned layers. To do this, they added the 3D material onto the 2D material in ultra-high vacuum, choosing growth conditions where the layers self-assembled in a reproducible orientation with specific degrees of twist. Having grown the materials, they then had to figure out how to reveal the atomic configurations and orientations of the different layers. A scanning transmission electron microscope actually produces more information than is apparent in a flat image. In fact, every point in the image contains details of the paths along which the electrons arrived and departed, as well as any energy that the electrons lost in the process. All this data can be separated out so that the information at all points in an image can be used to decode the actual solid structure. This process is only possible for state-of-the-art microscopes. The researchers used a combination of techniques called 4D STEM and integrated differential space contrast to achieve that process of extracting the full structure at the interface from the image. The researchers showed through modeling that electronic properties are expected to be modified in a way that can only be understood if the full structure of the interface is included in the physical theory. What the researchers found is that indeed this stacking, the way the atoms are stacked out of plane, does modulate the electronic and charge density properties. The findings could help lead to improved kinds of junctions in some microchips, for example. Every 2D material that is used in a device has to exist in the 3D world, and so it has to have a junction somehow with three-dimensional materials. So with this better understanding of those interfaces and new ways to study them in action, the researchers are in good shape for making structures with desirable properties in a kind of planned rather than ad hoc way.